Hi, in this video we are going to see an example which illustrates some of the nice properties of the Fourier series coefficients of real valued signals. We are going to deal with the Fourier series given in terms of the superposition of complex exponentials, and we are going to discuss the full wave and half wave rectified sine signals and the relationship between them. Now, we have already discussed these two cases in some previous videos. So we are going to remember first the values of the coefficients, and then we are going to consider the relationship between these coefficients. Now, first of all, how do we obtain the full wave and half wave rectified sine signals? Now, our starting point is the pulse P of t, which is the positive lobe of the sine signal from 0 to pi. So it is the magnitude of the sine signal is the amplitude is 1. So P of t is equal to sine t for t between 0 and pi and 0 elsewhere. Now we obtain the full wave rectified sine signal by repeating this P of t with a period pi. So it's the periodic extension of this P of t. So x, okay, we are going to write down the expression of the full wave rectified sine signal. This is equal to m from minus infinity to plus infinity, P of t minus m pi. Okay? So, the full wave rectified sine signal, we can draw the graph of this signal as follows. We have the periodic extension of the positive lobe of the sine signal. So from 0 to pi and then to 2 pi, 3 pi, etc. Okay. Now, we have, in a previous video, we have calculated the Fourier series coefficients of the full wave rectified sine signal as 2 over pi 1 over 1 minus k squared. K is running from minus infinity to plus infinity. Okay. So these are the Fourier series coefficients of the full wave rectified sine signal. Now the half wave rectified sine signal is the periodic repetition of, or periodic extension of P of t with a period 2 pi. So it is m from 0 to, m from minus infinity to plus infinity, P of t minus m 2 pi. In fact, here maybe before considering the half-wave rectified sine signal, in the full wave rectified sine signal, the fundamental period t0 of the full wave rectified sine signal is pi. So omega 0 in the full wave case, full wave rectified sine case, will be equal to 2 pi over pi. So it will be equal to 2. Okay. Now, for the half-wave case, the period is the fundamental period of the half-wave rectified sine signal is 2 pi. Therefore, the corresponding omega 0 for the half-wave case is 2 pi over 2 pi, which is equal to 1. Now let us also consider the graph of the half-wave rectified sine signal. Okay, I write it as a superscript, sorry. Half-wave rectified sine signal. So it is from 0 to pi, it's equal to 1. Here also it's equal to 1. And then it is 0 between t between minus pi and 2 pi, and then again it repeats. So we have the half-wave rectified sine signal. Now the coefficients, Fourier series coefficients of the half-wave rectified sine signal is evaluated in a previous video as follows. For odd values of k, for odd k, all ak will be equal to 0 except a1, which is equal to 1 over 4j, and a minus 1, which is equal to minus 1 over 4j. And for even values of k, ak is equal to 1 over pi, 1 over 1 minus 4k square. Okay, let me not forget the superscripts, denoting that these are the coefficients of the Fourier series coefficients of the half-wave rectified sine signal. So we have evaluated these coefficients, as I have told you before, in some other video recordings. Now here we observe certain properties of these coefficients. First of all, the full wave rectified sine signal, as you see, is real valued and even. and therefore the Fourier series coefficients are real valued as well, and AK is equal to A minus K. So we can just note this observation over there. The full wave rectified sine signal is real valued and it is even. That means x full wave t is equal to x full wave minus t. And because of this, since it is a real valued and even signal, AK are real valued and AK full wave is equal to A minus K full wave. Now, on the other hand, the half wave rectified sine wave is neither even nor odd. So we observe that for all odd values of k, the coefficients are 0 except a1 and a minus 1, which are pure imaginary, given by 1 over 4j and minus 1 over 4j. And for even values of k, the coefficients turn out to be real values. And also, we observe that when we replace k by minus k, we obtain the same result. Now, another interesting observation is when we compare the values of the Fourier series coefficients of the half-wave rectified sine signal for even values of k, we see a similarity between these expressions and the expressions of the Fourier coefficients of the full wave rectified sine wave. This is not a coincidence. So we have to, first of all, establish a certain relationship between the half-wave rectified and full-wave rectified sine signals, and there we are going to see why we have such a correspondence between the coefficients. So let us look at this problem now. Okay, now we can look at the relationship between the Fourier series coefficients of the full wave and half wave rectified sine signals. Now, for the full wave case, the coefficients are given by the following expression: 2 over pi 1 over 1 minus 4 k square for all values of k. Therefore, the half-wave rectified sine signal is equal to the Fourier series representation is k from minus infinity to plus infinity, 2 over pi 1 over 1 minus 4 k square e to j 2k t. Okay, now we are going to use this expression to interpret the Fourier series representation of the half-wave rectified sine signal. Sorry, this is full wave case. Now, for the half-wave rectified sine signal. Remember, for odd coefficients with odd indices, all the coefficients are 0 except a1 and a minus 1, and a1 is equal to 1 over 4j, and the corresponding complex exponential is e to jt, and a minus 1, which is minus 1 over 4j, e to minus jt, plus k running from minus infinity to plus infinity, but we are only going to consider the even values of k, because the coefficients corresponding to odd k are all 0 except a1 and a minus 1. So for k running from minus infinity to plus infinity over even values of the indices, the coefficients are 1 over pi, 1 over 1 minus k square e to j kt. Okay. So we have the Fourier series representations of both the full wave and half wave rectified sine signals written in terms of the superposition of complex exponential signals. Now, we observe a certain resemblance between the Fourier series coefficients of the half wave and full wave rectified sine signals. We have 1 over 1 minus k square here. We have 1 over 1 minus 4k square in the other one. And we have the multiplier 2. Now, okay. Now remember that any signal can be represented as the superposition of its even and odd parts. So we can consider this for the half wave rectified sine signal. So the half wave rectified sine signal will have its odd part and again the even part. And when we add these two, we obtain the signal, the original signal. Well, remember that in order to obtain the odd part, we do the following. We have the signal itself plus minus its time reversed version divided by 2, and for the even part we just add the signal, original signal x of t and its time reversed version and divide by 2. Now, let us see this in graphical form. Now, the half wave rectified sine signal has the following graph. Okay, this amplitude is 1 from 0 to 2 pi. 0 to pi, from 2 pi to 3 pi, etc. So this is the sum of the odd part. Now the odd part is nothing but 1 over 2 sine t. So the odd part of the half-wave rectified sine signal is just sine t, but the amplitude is 1 over 2 because of this 1 over 2 factor in the expression for evaluating the odd part. And the even part is, okay, this is a plus sign. The even part is simply the full wave rectified sine signal. Okay, the even part of the half wave rectified sine signal is nothing but 1 over 2. So this is again, this amplitude here is 1 over 2. 1 over 2 times the full wave rectified sine wave. Okay, so the half wave rectified sine signal is, the odd part is 1 over 2 sine t. But if we look at the first two terms of the Fourier series we have just written above, it is nothing but 1 over 2 sine t. Okay, so this is the odd part of the half-wave rectified sine signal plus the remaining part. Okay, the remaining part is k from minus infinity to plus infinity, 1 over pi, 1 over 1 minus k square e to j kt, and k is taking only even values. So this part is just the even part of the half-wave rectified sine signal. But if we look at the expression closely, so first of all, let us write down the odd part again, 1 over 2 sine t. The series over there can be written as follows. Now, since k is running from minus infinity to plus infinity over only even values of k, we can run the series from minus infinity to plus infinity, but we replace k by 2k, 1 over 1 minus 2k squared, which is 4k squared, and also in the exponent of the complex exponential we have 2kt. But we see that this is nothing but 1 over 2 the full wave rectified sine signal, which is equal to the even part of the half wave rectified sine signal. So there is such a relationship between the full wave and half wave rectified sine signals. Now, in the half wave rectified sine signal, we observe that the odd part has pure imaginary coefficients, 1 over 4j and minus 1 over 4j, and the even part, as expected, will have real valued coefficients because our original signal is real valued. So In this example, we illustrate the properties of the Fourier series coefficients for the case of real-valued signals. And in particular, in this case, we have considered the relationship between the half-wave and full-wave rectified sine signals. Thanks for watching.